Chapter 9, Question 9 is asking you to predict whether each of these ionic compounds would be soluble in water. So each of these are ionic compounds, which means that they are made of metals and nonmetals, and which means that they are ions, elements with charges, that are sticking together because of their opposite charges. So lithium has a positive charge, chlorine has a negative charge, and those opposite charges is what's keeping them together. Opposite charges attract. So when you put something like that, an ionic compound, into water, remember that water is very polar. Oxygen is electronegative, so it pulls the electrons in the bonds to itself. And because the electrons are going toward the oxygen, it becomes slightly, that's what that lowercase squiggly d, the lowercase Greek letter delta, means, slightly negative. Electrons are negative, and they're spending more time around the more electronegative element, oxygen. And because the electrons are going toward oxygen, they're not around the hydrogens as much, and the hydrogens are slightly positive. So that's what it means for water to be polar, that it has two ends to each bond, a positive end and a negative end. Okay, so when you put this ionic compound into water, notice that the attraction that was existing between these two, because of their opposite charge, now has competition. The positive lithium will be attracted to the negative water, and the negative chlorine will be attracted to the positive hydrogen. So it's a tug of war. Who will win? Who will pull, for example, the lithium closer together? Will it be chlorine, or will it be this oxygen? And the answer to that very much depends on the specific atoms involved. In other words, you would have to go into a lab and test it. You would have to know by experience which is stronger, the ion or the water. Now, if the water is stronger, then the compound would dissolve, right? The lithium would get taken away with the water, and the compound would break apart. In other words, it would be soluble in the water. But if the chlorine won, then these would stick together, and it wouldn't be soluble in water. Which one wins has to be tested by experiment. You have to go into a laboratory, put it in water, see which one wins. If you put lithium chloride in water and it dissolves, then it's soluble, and if it doesn't dissolve, it's not soluble. And that experience is summarized in tables like Table 9.8. So this is called a solubility table, and it's summarizing a bunch of people's experiments. Somebody went into a laboratory and put compounds with lithium in water, and they saw that every lithium compound dissolved. It's soluble if it contains lithium, unless it contains, and people have never found any exceptions. So you can use tables like this that summarize people's experience in order to figure out the solubility of any compound. So the way this table is read is, if a compound has anything on this left column, then it's soluble, with the exception of anything that also has what's on the right. So for example, anything with chlorine will be soluble, unless it's paired up with silver, lead, or mercury. Okay, so let's try to use this table with a few of these compounds. Lithium chloride. What will win, the chlorine or the water? So we see that anything with lithium is soluble unless, and there are no exceptions. So this is definitely soluble in water. Put a chunk of lithium chloride in water, and it'll dissolve. Okay, how about B, silver chloride? So you can look for either silver or chlorine. Start in the column on the left. A compound is soluble if it contains chlorine, unless it also contains silver, lead, or mercury. Oh my gosh, silver! Silver was one of the ones that is there. So this compound will actually be insoluble because you can see it has that silver. So this is insoluble, and what that means is you put it in water and it'll stay a solid chunk. It won't break apart and dissolve. Okay, next compound. C, barium carbonate. Barium carbonate. So we're looking for either of those. Start on the left column. Something is soluble if, and we don't see carbonate there. So now we can go to the right. Something is insoluble if it has barium. And the only time something with barium would be soluble would be if it had sulfate. So because this compound has barium, it's insoluble. So this would be insoluble. All right, how about K2O? That's potassium oxide. So we're looking for either potassium or oxygen. We see potassium is right here. Potassium is soluble unless, and there are no exceptions. So potassium is always soluble. Because it's soluble, it will dissolve in water. Put a chunk of potassium oxide in water, and it'll disappear before your eyes, just like chunks of table salt disappear before your eyes when you put it in water. All right, how about this? Iron 3 nitrate. Iron 3 nitrate. We're looking for either of those compounds. NO3, keep in mind, is a polyatomic ion, so we'll peel our eyes for that, keep our eyes out for that. Notice here's NO3. Interesting. It is soluble unless, and there are no exceptions. So this is always soluble. Anything that has nitrate is soluble, and so this compound will dissolve when you put it in water. And so that's how you can use these tables to tell which one wins, the attraction from the partial charges of water or the attraction from the ion that these elements are paired with in their ionic compound. You can use tables to look it up and predict it without having to do your own experiments. You can stand on the shoulders of the giants who did the experiments previously.